We all have our favorite cups for coffee, tea, and hot chocolate, but which cup really keeps your drink cold the longest? Today, we're hitting the streets and finding out what people think and then putting those choices to the test with some heat transfer science. What's your name and what cup are you drinking out of today?
Caitlin, and this is a paper cup. I'm Lizzie, I'm drinking out of the same cup.
My name's Alex Richmond, and I use a hydro flask.
My name is Connor Couch, and I'm drinking out of a Pure Life plastic water bottle.
What's your favorite cup to drink hot beverages out of?
Probably a thermos. Probably a glass mug.
A thermos.
A mug, like coffee in the morning, yes.
Okay, awesome. Thank you.
Yeah.
Okay, we've heard some great opinions, but now let's take these cups to the lab and find out which materials minimize heat transfer and keep your drinks hot. Time to get scientific.
Guys, I might not be able to do this.
Here's what we'll need for our experiment. Hot water,
Pot never boils.
thermometers, different cups, a stopwatch, and of course, Fourier's law to help us explain what's going on here.
Fourier's law tells us the rate of heat transfer, Q, depends on thermal conductivity, the area through which heat flows, and the temperature gradient. By rearranging the formula, we can solve for K. We're going to test how well these cups retain heat by filling each with hot water and measuring the temperature every 2 minutes. We'll estimate Q from the rate of temperature change over time, knowing the cup's dimensions and the heat flow area. Then, we can calculate thermal conductivity K for each material to quantify how quickly heat transfer occurs. Let's begin the experiment. First, pour boiling water into each cup and cover with foil to prevent heat loss from convection. Then, stick meat thermometers into each cup. For the first 10 minutes, record temperature every 2 minutes, then switch to every 5 minutes until 30 minutes is reached.
The noise is horrible.
That's it. They turned us a little bit. 124.7.
For glass, paper, ceramic, non-porous plastic, styrofoam, and double-stacked styrofoam cups, we measured and took note of the internal temperature using a meat thermometer and the outside temperature using a heat gun at various time intervals.
This one is 94 point.
What am I gonna do with this? And after 30 minutes, here's what our data looked like. Let's plot the temperature versus time graphs for each cup to visualize how heat transfer happens differently depending on the material. Notice how the slope of the temperature drop is steepest for the glass cup? That's because heat transfer occurs faster in materials with low insulating properties. The styrofoam, on the other hand, has a slower temperature drop, meaning less heat transfer. Further, the double-stacked styrofoam cup has an even slower temperature drop. Now, let's use our data to calculate K for the glass cup first. We'll first estimate Q, the rate of heat transfer, by the change in temperature over time. Then, by setting this equal to Fourier's law equation and plugging in all the constants we know, we can solve for K. Now, let's do it for the rest. And before I show the results, I want to acknowledge the few assumptions we made in the process to simplify our calculations, which may account for why our K values differ from experimental K values. And here's what we found. The styrofoam had the lowest thermal conductivity K, meaning it significantly slowed down heat transfer. With 2 layers, thickness increased, which further decreased thermal conductivity. On the other hand, the glass cup had the highest K, allowing heat transfer to happen rapidly. This is why you don't typically see people drinking hot coffee out of glass cups, and the same goes for heat transfer in. Smoothies and slushies are typically housed in styrofoam cups to prevent them from melting. This experiment shows how important controlling heat transfer is in everyday life. Chemical engineers use this knowledge to make better insulation, improve industrial heat exchangers, and even develop thermal protection systems for spacecraft. By reducing unwanted heat transfer, we can save energy, improve efficiency, and solve challenges in industries ranging from construction to space exploration.
Lift off.
Whether you're designing the next big thing for sustainable energy or choosing the best thermos for your coffee, understanding heat transfer is key. And remember, science isn't just in the lab, science is also in your hands every day.
Here's what we need for our experiment. Hot water, thermometer.
Day life. Chemical engineers use this knowledge to make better insulation.
Yeah. Depending on the day, no.